So phase two, table of contents, and this was not built um, on top of the phase one submittal, but I want you to do that so you've got consistency in your formatting and stuff. And so here's your water control product, and then you've got a couple of nice pictures, purchasing considerations, unit price, dimensions, purchasing quantities, product description, construction considerations, and I'll probably add into the rubric, a short descriptive paragraph that explains why you chose the products you did. Again, I want you to specify a climate zone, look at the code for that climate, and look at, insulatory values, stuff like that. Maybe look at perm ratings for your water control layer. We'll talk about that more when we get into water control, but or for your vapor control, rather, take into account how much humidity is in the environment and in the where you're designing for. Think about your window properties, and the relationship between window to wall ratio and R value and performance of your windows. We'll go over that. I think I went over that already. I did go over that already in the last lecture, but we'll hit that again today, and give you some stuff to think about as far as that goes. Again, you've got all these properties on your window, and you need to look at all of your control layers and how you need to detail this stuff. You need to have a continuous control layers, and we'll talk more about that when we do the pin test. So here's some good graphics and construction detailing sort of, and things that you need to take into consideration for your air control. And then it's got insulation in there, thermal control, and you've got good graphics here of some examples of these products, and then your sources and stuff. So I'm gonna pause this and make myself some notes. Does that make sense to everybody? Cool. Just to recap really quickly, we'll go back through these slides that we covered last time, but you guys were paying close attention, so we won't spend too much time. We've got envelope-based loading and typical internal and solar gains. So remember, envelope-based loading is stuff that's sort of not delayed, that the HVAC system has to deal with, and then some of your internal gains are not delayed, but some of those gains, like solar gain, is going to be delayed. The sun comes through your windows and heats up materials inside of the building, like concrete, for example, and that energy will be re-emitted later. So a lot of the time you have those delayed gains that later turn into loads. And we saw in the quiz stuff we went over just now, don't forget ventilation air is another source of thermal loading. We talked about ventilation air that's taken into consideration in energy models when we try to separate envelope loads and internal loads. Ventilation air is sort of in this gray area, but gets lumped in with the HVAC. It's not necessarily a load from the envelope. You have to have ventilation air and flush out pollutants and stuff like that. So we remember all of these priorities because we've looked at them a whole bunch. But remember, we're looking at window to wall ratio, increasing window performance, insulation, and have a simple and compact building form oriented to the sun. And this stuff is from your, this chart, or this list is from your book. You should have, probably they should have tightly sealed envelope on here and have air control as one of those, because you can have really high values of insulation in your wall. For instance, if you have super thick, if you do like 2x8 walls or something like that, and you have thick, bad insulation, if you use an air permeable insulation and you don't wrap your building tightly, your air control is not well done. You'll get what's called wind washing, and you will get air currents inside of your walls. And when you have air currents inside of batt insulation, it's reducing the effectiveness of that insulation to stop heat flow. When you have air currents, you're constantly cycling air and it's picking up heat from inside of your building, especially if it's cycling against just your interior finish. And if you don't have good air control, then it really reduces the effectiveness of your insulation. But we're shooting for the perfect wall. That's sort of our goal, and we'll talk about that in the next lecture. I was hoping we would get to it today, but I've been talking too long. Windows are the weakest link. Remember, 30 to 40% is where we want to be. I need to stop my share. That's why my thing's not working. Okay. Okay. Almost. My head screwed on straight this morning. Everybody see me drawing on the PowerPoint? Cool. Okay, so remember, this is one of the things that I want you to look at in phase 2 for your control layer practicum. We're looking at the climate and the heating degree days. And when you look at your window to wall ratio, what's going to be the safest thing to do when looking at your window to wall ratio and specifying the U value based on your window to wall ratio in the practicum phase 2 submittal. Can anybody tell me how you would approach that? What would be the easiest thing to do to get it right, other than looking at the code in your area? Because code's going to have a minimum performance value that you need to meet. And remember, the code is the lowest performance building that you can get away with. So, let's shoot for high performance. Can anybody just take a stab at it, take a guess as to what you're going to specify your window to wall ratio to be, since we're not doing an energy model, if we're going the prescriptive path rather than the performance path?
Window to wall ratio is usually 30 to 40%, correct?
Yeah. So easy, right? You just say, well, I'm going with that 30%, the sweet spot. And you don't need to look up heating degree days, but you can say 30% and maybe look at, if you specify it for 5, well, we can do that, and that's going to be our high performance window right there. Based on 5,400 heating degree days for climate zone 5, you need to have something with at least 0.4. Code may say something different, but that's a pretty easy way to do that. So just think about that and use that as your justification. Good.
So with these recommended values, does it matter if you were to use something that was even higher performance? Does it make a significant difference, or is the reasoning for having a 0.41 U value at a certain point just that you need to have that specific one for it to be viable?
Well, we have the model building code, right? And the model building code is what states design their code values off of, right? So we have a benchmark for energy performance, or a baseline rather. And so remember I think I said this on Monday, you know, depending on your building design and what you're trying to accomplish and whether it's residential or commercial, windows are the weak point. So it's always a good idea to get the highest performance windows that you can make a reasonable justification for. You know, you obviously don't want to get super duper expensive windows and then not have enough money to insulate your building properly. But you know, considering that the windows are the weak point, you know, there needs to be a balance, you know, financial balance between those two things, between your opaque assembly and between your window assemblies. But it's, you know, for the life of your building, it's always good to get the highest overall average R value for your envelope that you can. So, you know, if you have been in different places and you've been in houses where the windows are crap, you know, the windows in my house are crap. They're leaky. You know, any windows in my house that are double pane are no longer filled with gas, or they're cracked or something like that, and they're cold. I can feel cold air when I sit next to them. So, you know, the same holds true for new windows that are cheap. You know, they're gonna wear out or sort of fail early on. Even if you have good metrics in your windows and they're inexpensive or they're cheap, they'll fail earlier than, you know, a high performance, a good quality window. But you know, we have these sort of benchmarks for energy performance that we need to use. And you know, it's going to vary. Like I said, it varies based on the climate that you're in and what your goals are. But you know, this chart more than anything shows sort of the equivalent, the relationship between window to wall ratio, climate, and what the U values are doing as those things change, and to have the equivalent performance. So, you know, you can look at the code and specify what code dictates, or, you know, have some higher performance window. You know, it depends on, like I said, it depends on a lot of things. Does that answer your... So, blah, blah, blah. You know, all this stuff, we take all of this stuff into consideration when we're looking at wall, roof, and slab R values. When we're designing our building, here's some high performance values for the residential applications. You know, large buildings can get away with less wall ranges. Walls can range from R15 to R25 and be low energy. We talked about roofs and insulation, foundations and insulation, and this is where we got in the last class. So, you know, this was one of the quiz questions in the quantitative quiz, the first quiz from this week. So, you know, that's pretty straightforward. Just plug your numbers in from that quiz question. I think we did that in class. So here's a chart that looks at window to wall ratio versus the overall R value. And again, you know, you're looking at the same thing when your window to wall ratios are lower, and you have, you know, you can look at sort of lower or higher U values. So lower R values, lower performance windows, there's still that correlation between the overall wall R value. Remember, we're looking at the resistance of the material to energy transfer, right? So that's sort of the square feet is your material property there with R value. And then in U value, we're looking at how much energy is transferred across the material. So U value, remember, is BTUs on top. So, you know, when you get into the high performance window realm, you know, the same thing holds true. you know, the more windows you have, the lower your overall R value is for your assembly. So internal and solar heat gains, you know, these gains become more important and impactful when the envelope is well insulated. Okay, smaller buildings with residential occupancy are still envelope driven unless the envelope is really well insulated or the climate is very mild. So, you know, again, at some point, depending on the climate you're in, if you have enough money, there's going to be a point of diminishing returns for the amount of insulation that you have. And one of the people that we'll look at in here, there's a video, I need to post it to As You Learn, and I thought about watching it today, but obviously we're running out of time. Joe Stebrick, I think it's Joe. Anyway, the Stebrick guy that's one of the leaders in the building science industry, has some videos, and was looking at houses in Canada, and you know, some of that stuff is like at the forefront of the building science industry. And you know, in Canada it's way colder than where we are, right? But you know, he in the climate zone he was in, he said that point, you hit that point of diminishing returns at a foot of insulation, or like 10 inches of insulation, exterior insulation in the perfect wall that we'll look at later. But 10 inches of rigid insulation, I mean, think about the implications of that. Like, you have to attach your cladding to the structure of your building, right? So you have to go through 10 inches of rigid insulation to attach that cladding, your facade to the structure of the building. You know, so that to say, you know, you can spend a lot of money on your envelope, and you know, your windows and stuff like that, and that the point of diminishing returns is going to depend largely on climate and all of those other things. But so you know, we'll look at we'll look at a video that he does. Maybe I'll just post it and make a quiz for it next week or something like that. You know, large and boxy buildings will usually be driven by internal gains. We talked about that. So here's our equations from the book, and the way we quantify our building's design from an efficiency standpoint on how well it's designed with exterior surface area versus the volume. So, you know, this is from section 2.5 that discusses building form and orientation. And these are two different metrics to quantitatively compare different options on your building form. So this stuff is really useful early on in the design process. You can get a good idea of how efficiently you're using your space, versus, you know, the height of your walls, and the amount of exterior surface area. And remember, all of your surface area above grade and even below grade, but it's more true above grade. You have those delta T's that are driving the heat transfer across your envelope. So, you know, that's we have to spend money to control that heat transfer and stuff like that, and keep our building comfortable. So the more surface area you have above grade on your facade, on your building's envelope, the more expensive it's going to be, the more potential there is for heat transfer. So here we're looking at the surface area of each side of the building, the overall surface area. So, you know, in compactness, we're looking at, you know, typically we're looking at a cube, right? Or, you know, if you get real fancy, so there's going to be surface area of, I don't know if you can really tell where my dots are. That's not very useful, is it? It's the whole surface area, right? So pay attention to that. You know, if you have a rectangle, then you're not going to be able to just multiply it by 6, right? You're going to have to do this side and this side, you know, so that dimension times 2. And then I think maybe I can change the color of my pen. well, you get the idea. You know, you're not going to be able to multiply it times 6, so you got to do top, bottom, left, right, front, and back, essentially. So, you know, we get with surface area, easy, right? Basic geometry, length times width, and then do that 6 times, or 3 times if you have a rectangle. So, you know, you can have a building that gets a really good compactness number, but that doesn't have that much usable space, right? If your building has a small footprint, but it's super tall, you know, and you've only got 2 stories or something like that, you know, that stuff like high bay buildings can get a good number, but it doesn't have that much usable space. There's only 2 floors, right? And your footprint's small. So, you know, to account for this, we use our FE ratio. So this is gross floor area in square feet, right? Floor area in square feet, or feet squared rather, not square feet squared. And that's above grade, okay? Or the surface area, we take the surface area, sorry. The surface area is just above grade. We're not looking at the bottom of your poured slab or below grade walls or anything like that. It's just above grade. So when you see something that says floor to ceiling height of 13 feet or something like that, and you have three stories, you know, you can assume that that's a 39, is that right? 13, 26, 39 foot tall building, okay? Plus your roof, you know, that times the length and the width is your surface area, right? So, you know, the reason we're not considering below grade stuff is that delta T, we have a smaller delta T with surfaces that are touching the ground. So, you know, these numbers are trying to look at energy use according to the environment, whatever climate you're in. And this is a way to get a rough idea of that. Like I said, it's useful early on in the design process. And, you know, these 2 numbers are used in similar ways. And with them, we can compare buildings between forms. We can compare forms to one another, different forms to one another, and get an idea maybe of what we're going to be looking at in terms of energy use, and what our building performance might be based on the different forms. So, you know, for compactness, there's really only a 25% difference in, you know, the most compact building versus the most sprawling building. Compact buildings have a higher number. Sprawling buildings will have a lower number. So ultra low energy houses will have a C value higher than 1, and we're not going to do an example for the sake of time, but C values greater than 1 for ultra low energy buildings. Does that make sense? You guys can do geometry, right? Simple geometric calculations, looking at surface area and stuff like that. I don't need to go through an example, right? Okay, cool. And if you struggle with that, you know, we can meet outside of class if you need some refresher or something like that, or you can just Google it. Stuff's pretty simple. Your book gives examples of how to use this number to compare different design options. So here you have a 2-story square building, and then 1-story building, rectangle, crazy shapes. What does this building look like? Does anybody recognize this shape? Has anybody looked at floor plans of buildings on campus?
Is it the jet building?
Yes, very good. Yeah, so, you know, this stuff is useful early on in the design process, but I've spent a fair amount of time in the jet building, and I kind of hate it because it looks the same everywhere you are. And it's just, I think it's a stupid shape. I mean, it's a nice looking building, but you know, if you're not paying attention, it's easy to sort of get lost in there. So, you know, early on in the design process, you might have, you know, these different building forms that you're looking at, and you need some way to assess the difference between these building forms and what you can base on performance. So that's what these numbers are doing. And you'll notice these numbers are crossed out. It's a good idea when you're looking at values like this in your book, and to go through and to make sure you fully understand how they get their numbers and make sure that they're right. You know, a lot of us, you know, I've been bad for this or guilty of it myself until you start digging into some of this stuff and you're forced to dig into it. You know, you look at numbers on a chart and it's really well made and it's pretty and it's got good graphics and you're like, oh, well, it's got to be true, right? It's in a textbook. Not always the case. You know, people that wrote this textbook are just like you or me, and you know, we're human, we make mistakes, so that stuff's always good to check. So you know, when we're looking at our compactness number, our two-story building has a pretty high compactness number. Even the one-story is still at 1. And then as you get into some of these more longer or more complicated shapes, that number starts to go down. You know, so this is the number that allows us to quantitatively assess our building form rather than saying it's good shape, looks good, yeah, checks out, let's go with that design. You know, we can slap a number on it and assess it quantitatively. So, you know, with the FE ratio is a better building. So we've got 1.71 there. And, you know, this building is more compact. It's the same area, but it's more compact. And again, when you get into those longer buildings, excuse me, your number is going to start to go down a little bit. But, you know, and here's one of those examples of the high bay building, looking at, you know, the compactness or this FE ratio, the efficiency of the building design. Like it's got, you know, a fair amount of square feet, but it's really high. It doesn't have as much usable space as it could, right? And, you know, a two-story building with really high ceilings, you know, you're having to condition all that space inside that, right? You're not conditioning just below this point. You're having to condition all of this. And, you know, if you're aware of the fact, or maybe some of you have heard of thermal stratification, you know, hot air rises, right? So depending on your ventilation design, if you've got vents coming up from the floor, then you're going to have, you know, layers of warm air that will slowly rise, and it's going to be comfortable down here. But, you know, if your ventilation is up here and you're having to push air down, then it's not going to be as effective, right? Because hot air is less dense than cool air. So hot air wants to rise because it's more buoyant than colder, more dense air. So again, you know, the higher the FE ratio, the lower the EUI, the energy use intensity, which we know is a way that we compare buildings of different sizes. The lower the EUI for the building will be, because you have the more usable floor area you have, the lower that number becomes. So, you know, this is the reason that we have higher R values for homes, because they have lower FE ratios. So we're actually almost done. I talked way too long today. You know, our form, as we've seen, does impact our energy consumption. And, you know, larger buildings have, the form has less of an impact on larger buildings, right? So, you know, it sort of holds true. The same thing is true with our envelope. Our homes are more envelope driven, have more envelope driven loads. The form of our home matters more than it does in larger commercial buildings. because, where we have bigger systems and stuff like that, so on and so forth. You can get away with a little bit more when you're designing large buildings. So some of these, if you take sustainable building design and construction with Abilius, or, any of the architectural studios you get into, you see some of these pretty wild and, really amazing buildings aesthetically. These designers can get away with this stuff a little bit easier in larger buildings. So, daylighting and natural ventilation, cooling, again, we're talking about trying to use free forms of conditioning, whether we're lighting or heating, or, using natural ventilation with our building form. If you have a more narrow building footprint, then it's easier for, air to pass through one direction of that. If you look at homes in the South, we looked at this in 1708. That professor's gone now, but you look at like some of the old colonial style homes, they're more narrow, they're only a couple of rooms wide, and they're tall. And that, that increases the potential for ventilation across from one room to the next. When you have a narrow building, you've got more potential for air to move through it, rather than a really square, deep and wide building. Some of the interior spaces are not going to have as much airflow, but when you have just two rooms in a hall that separates them, and windows on the exterior, that are exposed to that wind outside and to air movement outside, the air can travel more easily across those rooms. So, you can get some free cooling that way. So, simple compact forms with short dimensions can be 45 to 60 and feet are preferred for low energy buildings. And, make a note, the higher the FE ratio, then the lower the enclosures area versus floor area. So this also means reduced envelope costs, right? The higher your ceilings, the more you're paying for stuff that you're not technically using. If you have 15-foot ceilings in your living room, sure, you can, use it and put glazing on it and have more light in your living room and have a more open and feng shui, or, whatever, a more open floor area, and feel happier in your home. But that's added cost. You have to insulate that stuff, and you have to condition it. You have to condition the air. You're not conditioning the air that goes up into those high ceilings, but the air you're trying to condition your occupied space with is going to go up there. So, it's going to increase the cost. So, when you have this type of layout, you can reduce the lighting loads in your building. And these occur mostly during the day when your building's occupied, in commercial. So, if I can use free light in my building, I can cut down on my lighting costs per square foot, the amount of energy that I need to use in my building, and the amount of lighting equipment. If your building has no one in it at night, and when you use lighting sensors and occupancy sensors, you can cut down on that even more. And so you can build a market cost high performance building if you do it using some of these tools. If you keep the form simple and more efficient, you can build a really high performance building at a normal market cost that's not exorbitantly expensive. And the FE ratio we're looking at right now, it often has a bigger impact on first costs than it does on energy consumption. The more sprawling and I don't know, the higher ceilings you have in your building, the more it's going to cost you. So it often has a bigger impact on the initial cost of the building, the upfront cost versus energy consumption. So that is it. Does anybody have any questions? We're going to stop right there and then get into our next lecture on Monday. Any questions? Seeing a lot of blank stares. It's Wednesday, guys. The week's half over.
This week?
What's up?
How many quizzes do we have this week? Do we just have the one that's big, or is it like two small
Two.
ones?
It's two
Okay.
small ones. So you've got the quantitative ones. Let's look at that. If you guys don't want to look at that, you're free to go. But those were the only questions that we didn't look at today on that quiz. I think it was the last two, and we covered those now with compactness and the FE ratio. So we looked at the heating degree days one. Have you guys, some of you have tried to do this quiz. Why isn't this working? There we go. Some of you said you already tried to do this quiz. But for those of you who haven't, tell me how to do this. What is the freaking problem here? Tell me how to do this first question again. We went over this in the last class. How do I get heating degree days? With my heating degree days units are delta T times 1 day. Who remembers how to do that?
Since your average point temperature is 65, you'll do 65 minus the 24.6 and get that value. And then you'll do 65 minus 39.6 and get that value, and then add up all those values for the 7 days.
Yes. R value is an easy one. How do we do that one? Somebody else that hasn't done this quiz yet. How do we get R value from U value?
Do you divide it by 1?
1 divided by, but yes, divided into 1. So 1 over 0.35 is going to be my R value. Good. We did this one. This formula made sense to everybody, right? That one's pretty easy. You just plug it into the formula. Number 4. Who remembers how to do number 4? That's easy. We did that in our math and physics quiz. We've got power, we've got runtime per day, and we want how much energy we use in a year. Somebody else answer that question that hasn't answered today, that knows. I know somebody out there does.
If I remember it, it's just the 75.2 times 24 times 365 or something like that.
There's one more step. We're looking for kilowatt hours.
And then you divide it by like 1,000 or something.
Yes.
Yeah.
Very, very good. Thank you. And then, we're looking at compactness, which was the formulas we looked at today. So volume, total volume over the surface area. So volume, length times width times height. And then surface area, you're doing length times width times 6 times essentially, depending on the dimensions of your building. If you have a cube, you can do it times 6, or you have to do it at least 3 times, right? And then the last one, I have too many things going on at one time. Oh, that didn't work. There we go. So the last one, we have 2 stories here. We've got a width. I'll figure out how to do this one day, or I won't. In every class that I teach, will have to watch me struggle through this. Life sucks, doesn't it? Just kidding. So we've got width, length, and a floor to ceiling height with 2 stories, right? So 2 times 12 is our floor to ceiling height. So our building is 24 feet high, and then we have a width and a length. So we just find our 24 feet times our width times 2, and then 24 feet times our length times 2, and then width times length times 2. So we had to do that 3 times, right? So not too difficult. And that's it. So, you know, if any of you need any of this stuff explained in a little better detail or something, you know, schedule office hours with me, or, you know, if my office hours don't work, I'm always happy to meet with you guys outside of office hours if we can find a time that works. Don't forget to go to, you know, try to go to the career fair next Wednesday. And I'll remind you again on Monday, start looking at some of those companies that are coming. You know, you juniors and seniors should either be looking for internships or a job when you're going to graduate if you haven't already found one. You know, now is the time to be doing that and making these connections. If nobody else has any questions, then that's all I got for today. Thank you for your attention, and thanks so much for coming to class today. And I'll say I'm really, you know, this being my first semester teaching, I'm shocked at how good my 8 a.m. class is. You know, I thought that in classes that I had at 8 a.m., maybe it's because I'm just not a morning person, but my brain usually doesn't work as early at 8 a.m. So you know, this has been really cool to have an 8 a.m. class with so many people that are actually paying attention and getting the information and the stuff that I'm spouting at you on a regular basis. So thanks for that. Good job, guys. Thanks again, and have a great rest of your week. And, you know, I'm around. Send me an email if you have any questions or anything like that. Thanks.
On As You Learn, I just see one quiz that says enclosures for low energy.
It's hidden. I forgot to unhide it. Thank you.
Uh-huh.
Very good. I'm glad you caught that because I totally forgot.